Wonkyo Choe is a second-year PhD student at the University of Virginia, working with Professor Felix Lin. His research interests lie in the broad computer systems area, from low-level to high-level applications. He's currently focused on the optimization for autonomous driving systems. And today he's going to talk about his work, STI, turbocharging NLP inference at the edge via elastic pipelining.
Thanks for the invite. Hi, my name is Wonkyo Choe. Today I'm going to talk about STI NLP inference at the edge via elastic pipelining. So NLP is, as you already may know, that it's a process to understand text and spoken words. So there are multiple ways to process this, but especially our scope is on-device NLP inference. So on-device NLP inference is a part of process, or it can be a system services. Usually one task requires one language model. There are a few popular NLP inference examples. For example, sentiment classification, it distinguishes whether the sentence is sad or happy, or question and answering, it analyzes the given text and gives an answers. So compared to the cloud offloading NLP process, on-device NLP inference has several benefits, such as users can be more private, can receive the fast results from the application, and use the application in any time, in anywhere. So there are multiple NLP models, but the recent trend is to use a transformer-based model. So the transformer is one building blocks that constitute a layer in a neural network architecture. So in high-level context, what it can do is that it helps understand the given text and spoken speeches better. There are two popular NLP models, generative model and classification. What we focus on this paper is text classification, or BERT. Due to the importance, it now requires machine learning model. Although the transformer-based model can be used in mobile devices, it follows a few high resource demands. First, large language model size. The size of language model, on the keynote, the size of language model keeps growing nowadays. This is because it is designed to be over-parameterized. For example, BERT has 440 megabytes, this BERT has 170 megabytes. So the rationale of such a huge size is due to accuracy. If the model has more parameters, then it often results in a high accuracy. The second, the resource is low latency. Most users expect that application gives a result within a few hundred milliseconds, but large language model size impedes this goal. So considering such resource demands of on-device inference, we found that it is challenging to have a best scenario to make for 3 different resources on mobile devices. So we started this project by asking ourselves that how do we efficiently execute NLP inference, respecting target latency and maximizing inference accuracy, and adopting available memory in operating system at the same time. So there are a few prior works to try to achieve similar goal. First one is holding memory. It just keeps model always the memory. The benefit is its execution starts immediately, but the downside is that it significantly increases the memory footprint. The model size is often bigger than the application size itself. Second, load before execution. It loads the model from the flash storage just before the execution. So the benefit is that it's increased a little bit of amount of memory footprint thanks to the on-demand behavior. However, since the full model is loaded every time request happens, so it incurs a long delay. For instance, this BERT takes 3.1 seconds versus inference only takes 0.6 seconds. Then what about the pipeline? Pipelining is that it executes and load models in a layer-wise. So the advantage is to overlap the I/O and compute so that we're hiding the I/O latency a little bit. But there is still pipeline bubble still exists. In other words, computation is still underutilized. So why this is happening? Because of the I/O compute skewness. In this BERT, I/O loading takes 3 times longer than the computation time. The reason behind it is that because of the each attention layer has a low arithmetic intensity. In other words, the computation finishes quickly, and at the same time, mobile storage I/O is often relatively slow. So to overcome problems mentioned in previous works, we proposed elastic pipelining. then let's look at the figure. So each number indicates that the resource block per layer, and the compute block means time to compute, and the IO block indicates the IO loading time. And the red area is called the bubble, is computation, or IO is idle. So before applying our techniques, the system executes a few blocks or layers within the target latency, but ours can execute the maximum computation within the target latency, like squeezing a certain surface of the sponge with a few fingers. Our system can squeeze a certain layer of I/O blocks elastically, so that the system can minimize the pipeline bubble and at the same time maximize computation. So to do this, we propose two techniques. One is model sharding with a mixed bit width. Second is elastic I/O compute pipelining. In short, we can achieve the lower memory footprint and gain a higher accuracy at the same time. So let's look at our system workflow. So first stage is offline stage. It first provides hardware capabilities such as how much computation and I/O takes in a per layer. And after profiling, we do a partitioning, a language model. So we use model sharding to manage multiple versions of shards. And then during the online stage, given the profile data, the planner generates the submodel execution, such as how many layers, how many shards, and what kind of version should be executed within the target latency. So once the system confirms that the generated plan is valid, then the plan will be executed in the pipeline. So let's look at our technique first. Offline stage, model sharding. Our objective is that to eliminate I/O compute skewness and at the same time find control I/O and compute ratio. Below figure is an overview of model sharding. We leverage existing work by selecting a subset of the layers or using the fraction of the layer. Even though we use a partial part of the layer, we still can get a meaningful result. So there are three steps for model sharding. First step for the model sharding is vertical partition. The system partitioned into m vertical slices or shard. Each vertical slice is independent and constitutes one attention head in transform layer. And second, we use quantization. The system quantizes each of the n by m shard into k-bit width versions. This allows our work to prioritize I/O resources at much finer granularity. And then lastly, the system does store each shard in total m by k shard on the disk. So with sharded models, the system is now able to plan and execute the task pipeline. To do this, we propose elastic pipeline planning, which is divided into the two stages. So the first stage is compute planning. The goal is that to max out the computation within the target latency. So how we do that, the system searches for the sub-configuration or sub-model and layers by m shard and fill this sub-model into the time budget. So the below figures are examples of the candidate sub-configurations. The first one, it has 3 layers by 5 shard. Second one has 2 layers by 7 shard. To select between 2 sub-models, we use heuristic method that picks the most deepest layer. The reason why we prefer depth is because each layer has redundant shards. So next stage, so the system has chosen n layers by m shards, and now need to select the k versions of each shard. The key goal is to use maximum I/O resources and no stall pipeline execution. Then how we do that? We'll just pick the most important shard per layer, considering I/O budget and shard bit width. So briefly, our planning set time budget for each layer. The red arrow indicates that budget before a certain layer block is executed. Invariably, I/O should be loaded before the execution. For example, if the system needs to execute or to compute layer 6, then I/O in layer 6 should be loaded before execution. So after setting the budget, we place different bit width shards for each shard in each layer. For instance, the system may choose for the layer 6 different combination of 2-bit, 3-bit, 6-bit, or 32-bit while keeping the time budget. So we've talked about the technology. We evaluate our system on multiple edge devices on Android or just Nano. And for model, we use Dynabird and Lizabird and evaluate a popular NLP benchmark at school. So let's look at the end-to-end result. X-axis means preload buffer, and Y-axis indicates accuracy, and the result is done under 200 millisecond and CPU. So first baseline is holding memory, and it has a high accuracy because the model always the memory, but as you can see, it takes a large memory consumption. Second, night pipelining. This has a small memory footprint thanks to the on-demand model loading. However, due to the I skewness, in this case, the computation is underutilized. Therefore, the accuracy is inferior to the holding memory. Third, we try to quantize and applied in each baselines. However, this process is still lower than the holding memory because IO's compute skewness still exists, and in this case, IO is underutilized. And lastly, our system achieves an optimal balance between memory consumption and accuracy. So at the cost of just only 1 megabyte, it achieves comparable accuracy to the holding memory and higher accuracy compared to the night pipelining or the night pipelining quantization. So there are more results on different benchmarks and different hardware setup, but due to the time limit, please see detail on paper. So to wrap up, in this talk, we present our Nova system, STI, a runtime execution model for on-device NLP inference. This will contribute two techniques. One is model sharding with the mix-to-mix width. A second one is elastic pipelining planning. So with these two techniques, our system reduces memory footprint 100 times less than approximately holding memory and gains the compatible accuracy. So thank you.